So my name is Lingzhi Sun. I'm currently a postdoc at University of Hawaii. So today I'd like to talk about our polarized spectroscopy measurement and using it as a new tool for characterizing water in planetary materials. Next slide, please. So let's start with a little bit background on polarization. So if you imagine a plane, or you can just look at the schematic diagram here, that's defined by the light source, the sample, and the observer, then this plane is basically parallel to the screen you're looking at. The light that oscillates parallel to this plane is the parallel branch, and the light that oscillates perpendicular to this branch is the perpendicular branch. So that's the linear polarized branches. And the received light, we can detect them at two directions. Then basically the perpendicular branch you observed is mostly from the specular reflection and half of the volume scattering. And the parallel branch is from the volume scattering. And next slide, please. So to explore this possibility of detecting water using polarization, we measured two kind of samples with a modified FTIR. We added a linear polarizer to the front of the lens. You can see on the figure in the upper right. And we use a sample stage that can measure both hot sample at 100 C and cold sample at room temperature, which is around 20 degrees C. So we prepared calcium fluoride that is infrared optical window that is designed for using 3 micron measurements and contains no detectable water. The other one is Opal A sample that contains around 10% internal water. And to avoid spectral saturation, we diluted the Opal sample with 10% calcium fluoride. Then we wet sieved all the samples into 5 grain size fractions, and you can see the samples in the lower right figure. And let's go to the next slide. So before we measure the spectra, we heated the samples at 100 C for calcium fluoride and 280 C for opal samples for at least 12 hours. Then we staged sample on the sample stage and measured the spectra while heating it at 100 C to avoid atmospheric water to deposit on our samples during the measurement. Then we derived the hot spectra. Then we let the sample to cool down at room temperature for 12 hours so the atmospheric water can be absorbed to the surface of the grains. Then we measured the spectra under room temperature and derived the cold spectra. And let's go to the next slide. And here are the spectra we derived for calcium fluoride and opal. So let's focus on the left columns for now. So those are the perpendicular, which is the first column, and the parallel branches, which is the second column. So the top panel is the calcium fluoride and bottom panel is for opal. We observed some similar trend for both of the samples, although they have very different internal water content. So first is that if you compare the hot spectra in the first row to the second row, which is the parallel, which is the cold spectra, there's an increase in 3 micron absorption, meaning the water increase has been captured. The same thing for the opal sample. This is in the if you compare the third row to the last row. We think that's because the volume scattering can capture more water than the surface specular reflection, and the perpendicular branch was diluted by the specular reflection. So it's showing less water content. And another thing is that this is if you compare the perpendicular branch to the parallel branch, which is the first column compared to the second column. The parallel branch shows a stronger 3 micron absorption, and this is because they're seeing more water from volume scattering. And if you compare the hot spectra to the cold spectra, for calcium fluoride and opal, you can also see increase. That means the increase in water adsorption has been captured by both branches. There are also some difference between the two samples. So if you look at the calcium fluoride spectra on the top panel, so from purple, blue to red, these are grain size increasing trend. But if you look at the spectra, smaller grain size of calcium fluoride show a stronger absorption depths at 3 micron. And if you look at the opal sample in the bottom panel, the smaller grain size show weaker 3 micron absorption. So we think that for calcium fluoride, this increase with decrease in grain size in 3 micron absorption is because the surface area to volume ratio for smaller grain size is larger than the large grain sizes. And for opal sample, this opposite trend to the calcium fluoride is because this large amount of internal water inside the opal sample. So this will show something similar to what we will see in minerals. So larger grains has larger amount of water. And let's go to the next slide. We found something interesting. If you look at the last column, so those are the ratio spectra of the parallel versus perpendicular branch. So for the calcium fluoride, if you look at the top two figure in the last column, the difference between the grain size seems to have been minimized, except for the largest grain size that's kind of divided from the rest of the data. So the rest of the grain size, the smaller grain size fractions, show basically similar spectral absorption among all of the grain sizes. But if you compare the hot, which is the top figure, compared to the second figure, you will see that there's still increase by water adsorption. So meaning this ratio spectra is capable of detecting water without without knowing the specific grain size distribution, but still it's capable of detecting water increase in 3 micron. And if you look at the opal spectra, it can show a very different trend. So in the last column, the bottom two figure, we see an increase in the 3 micron absorption with grain size. So when there is water and there isn't, this ratio spectra show very different trend with grain size variation. Then another thing we observed is that, you can see this 3.4 micron absorption on the perpendicular and parallel branches in the first two column spectra. But this feature seems to have been minimized. So this 3.4 micron feature is caused by the CH vibration in organics, meaning using this ratio spectra, we can detect stringent water absorption, but the organic absorption can be suppressed.
You have 1 minute left.
Oh, perfect. Next slide, please. So I applied an MGM analysis on the ratio spectra, and you can see that calcium fluoride is the diamond symbol, and the opal spectra is the circular symbol. There's a very different trend between these two samples. So calcium fluoride basically showed no variation with grain size, but the opal sample saw this very large variation with grain size. And let's go to the last slide. And here my conclusion. I'll just leave it here. I'm happy to take questions if I still have time. Thank you.